Okay, thanks so much for the introduction. It's really great to be here today, everyone. I'm the founder and CEO of a company called Frustum Inc, and we're entirely focused on bringing functional generative design to market through some really interesting technologies that I'm going to share with you today. But mainly what we say is we're this catalyst for bringing about the transformation of CAD design from iterative to generative. And for that, I think if you look at these parts that I have up here on the right and the left, they would just be very hard to manually model. They're both topology optimized, and they're directly output from our core technology. The one on the top right is traditional topology optimization of a piston. And that is to say constraints which an engineer specifies, user requirements, are taken into consideration in a multi-physics simulation. And the geometry is automatically produced. That's generative design. And the one on the left is very similar to that process, but some very complex structures have also been applied as what we call a design filter, which are for conformal lattices, another type of generative design that's becoming more popular. In our system, we can create both, and we can analyze them, and we're bringing more and more of this functionality to market. We have a few partners we work with. We're working with Siemens and Onshape, and look for more of our core capabilities in and around those products as we move forward. So why generative design? There's a lot of reasons, and I think that a recent article I have in Forbes, if you're curious, look it up, details some of the impacts of supply chain disruptions, which I think are fascinating. But overall, what does it mean to us as designers and companies? Lowering human capital expense per product. So that doesn't mean to say there's less engineers. There's just less time on the product spent to make something highly complex. Delivering better products faster. We're moving into a higher complexity future of engineering, where if you take 1 pound out of a plane, it'll amount to $10 million of fuel savings across an entire fleet per year. So the impact, even so small, thanks to generative design and additive manufacturing, can really be profound. Driving advanced manufacturing. We have these great new tools. I just saw the Mark IV booth outside, and it's so cool to see them going into metal. The impact of that is phenomenal, right? More pinpoint manufacturing, on-demand manufacturing. But why would we make the same old parts with a really exciting new advanced manufacturing technique? So what we're hoping for is that our technology will help drive that higher complexity future. So just for example here, these are two designs, one on the right and one on the left, that are both automatically created by our technology. The one on the right has 0 manufacturing constraints on it. It's essentially just free-form topology optimization, and the point here is that the designer only had to specify their user requirements and click generate, and that is what came out of the system. Same goes for the one on the left, but it has some extra constraints put on it, because maybe they wanted to reduce the amount of support structures needed or make it a milled part even. Yeah, we also don't ignore that we have other manufacturing techniques out there. So we make generative design functional. That's our goal as a company. We have two technologies. One is our product. It's a full cloud product like Onshape. It's called Generate, and it's intended to enable really fast and iterative work with generative design. The other is called True Solid. That's our geometry kernel. We really recognize that in order to do generative design, we had to have a new type of representation for geometry, or at least one that's not as popular as surface representation. And that's volumetric representation. So if you think of the old way of doing CAD, or the state of the art, you're defining a lot of surfaces in order to define a volume. In our world, that would be intractable if you're going to handle a lot of complexity. So we created True Solid in order to be able to represent it as a solid, a true solid, which surfaces are then created from. So we have a bunch of smart algorithms to do that. So Generate, it's a full cloud application, like I mentioned, like Onshape. It's for topology optimization now, but look out for more features as we go. And you can use it to optimize hundreds of designs in parallel. And that's really what I think is fun about it. So I'll demonstrate that today. After I demonstrate that, I'll lift the hood of the car, so to speak, and we can take a look at the guts, which is true solid. So it's a volumetric geometry kernel, as I mentioned. It's ideal for generative design. And surfaces are created from volume data without user interaction. So that's an automatic process, which is very important if you're going to make really crazy geometry like this. So demo time. I'm going to show Generate first. And if you're curious about trying out, it's free to use. Just go to our website, frustum.com. And if you scroll down here or click here, you can register for an account. It's a web application. But with it, you'll be able to do topology optimization now. And within about 6 months' time, you'll be able to use some of the more sophisticated capabilities for these types of minimal surfaces and lattices. So first, you just have to make an account. I'm not going to do that myself right now because I already have one. But it is web app based, so you'll need to do that. So it's already open here. And when you first use Generate, you have some sample projects down here which you can learn from. And I highly recommend doing that if you're excited about this. So just click this clone button, and it'll copy it into your projects. So I have one copied already. We tried to keep this interface really clean, and it is a very new product. We have releases coming out maybe every 3 months sporadically, but this is what you'll see when you clone a project. You have this workspace over here for design constraints, boundary conditions, and then once you start running an optimization, that will pop up, and you can monitor the progress there. We also have this terminal that outputs errors as they may come up from time to time to inform you how to use the product better. And you click this button here if you have an error, and it'll send it directly to us. On the right, we have this design space, which you can load from your CAD file. So if you're using Onshape, you export it as a step file, and you can put it directly into Generate. Once you have it in there, you can start applying these boundary conditions. So typically, these are engineering specifications. So what I've done is I've selected faces here, and I've applied fixed constraints. And then I've also put a load on this, which is represented by this vector. So this is mandatory in order to do topology optimization. I have 4 load cases, in fact, here. But on this specific optimization, I only have boundary conditions set without design constraints. So what I'll do is I'll just run this. A few options pop up about how much fidelity you want in this design. I'm just going to say yes, Generate. And now that process is not running locally on my computer. It's up on the cloud. And that's really where the power of this comes into play, because while that's running, I can open up other optimization scenarios and run them all in parallel. So we're really trying to leverage computing to get generative design sped up. This one I've put on a extrusion constraint, which is going to make this geometry extruded down to the base. That could be good for a self-supporting 3D printed part or a CNC milled part. And then I have another one here, which is unconstrained, except it's going to be higher resolution. And then the last one I have here is going to have reduced support structures by filling any cavities that may appear in the profile of the part. And again, those are all just specified in these design constraints. So now I'm really using the cloud. I have 4 processes running right now. I could do this on any number of projects. So we really hope to free the designer up to experiment in this way. And as these run, you can go do work on other things or check in on them. This one's, in fact, almost finished, so we can see what it looks like. And while that loads up, we can then go on and look at true solid and see how some of those modeling features work. So yeah, this is our first result. This is a lower resolution result. But what you can see here is the geometry kernel really at work doing the heavy lifting of modeling these surfaces for you. So that's, we think, very impactful for making generative design functional. All right, so we'll come back and look at these other designs as they finish, but let's dive into true solid. So this is running locally on my computer, and this is what our developers use in order to test out new features we're working on. And then over time, you'll see more and more of these features make it into our product Generate. So what we have here is a typical geometry tree, and I'm just going to make a primitive real quick. And it's a box, which I'll give some height to. Nothing special. You can make a box in any other CAD platform. But where it gets interesting is imagining the extra complexity. So let's also put a cylinder in with this box. And I'm going to make it a little bit wider here. So now we have a solid geometry without any surfaces specified. Those are being created automatically. But they're unioned together. And I can actually change the relationship of this union. So through influence. And this is really the problem that we've solved. How do you blend solid geometry together with pinpoint accuracy? So this is a blend with an exact radius. And that wasn't something available before through volumetric geometry kernels. So imagine now if you have many generative design parts they all need different blending profiles and radii. That can all be done with a single parameter or as many as you need. We can also change the relationship between these parts. So let's just make that a union. And I've subtracted from it. Additionally, I can change the relationship to be something that would help to make, say, a countersunk bolt hole. And now I have a chamfered part. So these are all just ways to control the geometry here. But what I want to do now is go up a level in complexity, which is what this is all about. So combining these parts again, and then changing the relationship of them to this softer fillet, we are back where we started. And what I'm going to do is put a higher level algorithm on top of that box for a gyroid. These are known as minimal surfaces. So for all these complex algorithms and filters, you have to carefully calibrate your parameters to get exactly what you're looking for. And that should do it. So really, with great accuracy now, I'm blending traditional mechanical geometry into geometry which is just impossible to model by hand, and doing it without surfaces, doing it by volume. And all of this is an output which I have control over, so if I want to make that ready for manufacturing, I'll just kick the resolution up, and now I'm getting a little bit more fidelity on those surfaces. So when you're modeling with solid geometry, it's very different than surface-based geometry. Solid geometry allows you to increase the resolution as you need it. So, it's a different type of workflow. And just a little under the hood of how this all works, I'm going to turn on a slice plane here and just give you a little window into the complexity of our world. All of these can be sliced out for 3D printing, and it's a really interesting way to model. But what you're looking at here is, it's kind of like gravity and density. And this is how we control all of these relationships through smart algorithms which affect this gravity. So with that said, let's look back at some of our optimizations over here. And I hope that you can extrapolate and imagine how these tools will impact our current product. So this one here is finished, and it had the extrusion constraint on it. So it's been projected all the way back down to the base plate here. I'm going to open that one up over in the core after I turn this slice plane off. And now I have that part again, but I've already pre-populated it with those really intricate minimal surface structures inside of the part. And I think that once you can imagine using these tools directly from the product, you can really get some high impact, highly complex parts. And why would somebody do this? This is a really good example of how to make sort of drain holes for all that powder that's in there while still lightweighting the part, but actually making something that's very manufacturable from an additive perspective. And additionally, just a little icing on the cake, this can all, of course, be simulated. So I already have all those loading conditions from Generate in this part. And here we are. I have all the displacements and so on here. And this, we can crank up the resolution to be a very high amount of accuracy. But you are seeing it pick up the stress concentrations and risers right where you'd expect it to for each load case. So more coming to Generate soon in terms of multi-physics. Stop by our booth. We're right outside. I'd love to get to know you all more and give you demonstrations as needed. And yeah, I look forward to bringing exciting generative design tools to all of you in the future. So thank you very much for having me.